Hi guys, my name is Fuyao Li, and I'm a senior student majoring in mechanical engineering. My presentation today is about the second chapter in the book, which is called Development of Additive Manufacturing Technology. Alright, let's get started. The first thing we need to know about additive manufacturing, I will call it AM since now for short, is that it was not developed in isolation. Instead, it came about as a result of developments in a variety of different technology sectors. Especially, it takes full advantage of many of the important features of computer technology. Without computers, there would be no capability to display 3D graphic images. Without 3D graphics, there would be no CAD. Without this ability to present objects digitally in 3D, we would have a limited desire to use machines to fabricate anything but the simplest shapes. So it is fair to say that without the computers we have today, we would not have seen AM develop. I have concluded the main constant in the chapter and divide them into four parts. Let's take a look at the first part, which is called computer-aided design technology, which is the main technology associated with AM. AM technology primarily make use of the output from 3D solid modeling CAD software. I believe most of us should have familiar with some of these softwares like SolidWorks, AutoCAD, LabVIEW, and so on. CAD technologies are available for assisting in the design of large objects as well as very small size, even to nanoscale. Also, CAD systems may contain rules associated with such behaviors that allow the users to focus on design and functionality without worrying too much whether a product can or cannot work. What's more, it allows the user to focus on small features of a large product, maintaining data integrity and ordering it to understand how subsystems integrate with the remainder. With the development in computer technology and the improvements in the way CAD data is presented, manipulated, and stored, most CAD systems can now quite readily run on PCs. CAD technology has rapidly improved in the listing regions: realism, usability and user interface, engineering content, speed, accuracy, and complexity. Well, it is quite possible to directly manipulate the CAD file to generate the slice data that will drive an AM machine, but this would mean every CAD system must have a direct slicing algorithm that would have to be compatible with all the different types of AM technology. Alternatively, each AM system vendor would have to write a routine for every CAD system. Apparently, both of these are impractical. The solution is to use STL file format. It can be accessed easily by all CAD vendors and now is a standard output from nearly all solid modeling CAD systems and has also been adopted by AM system vendors. This picture is an illustration. It uses triangles to describe the surfaces to be built. Each triangle is described at 3 points and a facet normal vector indicating the outward side of the triangle. Aside from the computer technology, there are a number of other technologies that have developed along with AM that are worthy of note. So the second part is about them, since they also have served to contribute to further improvement of AM systems. They are lasers, printing technologies, materials, computer numerical controlled machining, the use of lasers. Well, the last one is more like a principle of AM instead of technology, but I concluded here as well. There are two kinds of laser processing used in AM. They are curing and heating. With photopolymer resins, the requirement is for laser energy of a specific frequency that will cause the liquid resin to solidify or cure. Usually, this laser is in the ultraviolet range, but other frequencies can be used as well. For heating, the requirement is for the laser to carry sufficient thermal energy to cut through a layer of solid material, to cause powder to melt, or to cause sheets of metals to fuse. Earlier AM machines used tube lasers to provide the required energy, but many manufacturers have more recently switched to solid-state technology, which provides greater efficiency, lifetime, and reliability. Inkjet or droplet printing technology has rapidly developed in recent years. Improvements in resolution and reduction in costs has meant that high-resolution printing, often with multiple colors, is available as part of our everyday lives. Excuse me. Initially, colored inks were low in viscosity and feed into the print heads at ambient temperature. Now, it is possible to generate much higher pressures within the droplet formation chamber so that material with much higher viscosity or even melting materials can be printed. Let's take a look at this picture. It is a print head used in AM technology. As we can see, it is a relatively compact device with all the droplet control technology highly integrated into it. And these print heads make it possible to produce low-cost, high-resolution, high-through output AM technology. Earlier AM technologies were built around materials that were already available and that had been developed to suit other processes. However, the AM processes are somewhat unique, and these original materials were far from ideal for these new applications. The good news is, as we came to understand the technology better, materials were developed specifically to suit AM processes. They have been tuned to suit more closely operating parameters of the different processes and to provide better output parts. As a result, parts are now much more accurate, stronger, longer lasting, and it's even possible to process metals with more AM technologies. One of the reasons AM technology was originally developed was because CNC technology was not able to produce satisfactory output within the required timeframes. CNC machining was slow, cumbersome, and difficult to operate. AM technology, on the other hand, was quite easy to set up with quick results, but had poor accuracy and limited material capability. So for geometry that can be machined using a single setup orientation, CNC machining is often the fastest method. For parts with complex geometry of parts, which requires a large proportion of the overall material volume to be machined away, AM can be used to more quickly and economically produce the part than when we using CNC. As I mentioned before, the use of layers is not technology. Instead, it is more likely a key enabling principle of AM part manufacture. But it is really important, so I concluded and put it here. Almost every AM technology builds parts using layers of material added together, and certainly all commercial systems work that way. Primarily due to the simplification of building 3D objects, you can use the picture as an illustration. There are numerous ways to classify AM technologies. A popular approach is to classify according to baseline technology. Another approach is to collect process together according to the type of raw material input. Well, the problem with this too is that they may end up with weird combinations or may appear to produce similar results which end up with being separated. When there's a problem, there will be a solution. An excellent and comprehensive classification method is described by form, which uses a two-dimensional classification method as shown in this picture. The first dimension relates to the method by using the layers are constructed. In another dimension, form uses four separate material classifications: liquid polymer, discrete particles, melting material, and solid sheets. Let's talk about each of them some more. Liquid polymer systems. The first commercial system was the 3D system process based on liquid photopolymers. A large portion of systems in use today are in fact not just liquid polymer systems, but more specifically liquid photopolymer systems. Discrete particle systems. Discrete particles are normally powders that are generally graded into a relatively uniform particle size and shape and narrow size distribution. By using this technique, the binders can be ejected from multi-nozzle printheads. Binders coming from different nozzles can be different, and therefore subtle variations can be incorporated into the resulting part. The most obvious of these is the color that can be incorporated into parts. Melting material systems. Molten material systems are characterized by a preheating chamber that raises the material temperature to melting point so that it can flow through a delivery system. Printer technology has also been adapted to suit this material delivery approach. Solid sheet systems. One of the earliest AM technology used a laser to cut out profiles from sheet paper, supplied it from a continuous roll, which formed the layers of the final part. Layers were bounded together using a heat-activated resin that was coated on one surface of the paper. Once all the layers were bounded together, the result was very much like a wooden block. A hatch pattern cut into the excess material allowed the user to separate away waste material and reveal the part. What's the current looking of AM technology around the world? And what are we expecting in the future? Let's take a closer look. Earlier patents were filed in Europe, USA, and Asia, almost simultaneously. In early years, most pioneering and commercially successful systems came out of the USA. Companies like 3D Systems and J Corp have spearheaded the way forward. These companies have generally strengthened over the years, but most new companies have come from outside USA. In Europe, the primary company with a worldwide impact in AM is called EOS, Germany. Companies from France, the Netherlands, Sweden, and other parts of Europe are smaller, but are competitive in their respective marketplaces. AM technology has also been developed in Asia. In the early 1980s and 1990s, a number of Japanese companies focused on AM technology. This include large companies like Sony and Kira, who established to build AM technology, also became involved. Korean AM companies are relatively new, and it remains to be seen whether they will make an impact. There are quite a few Chinese manufacturers who have been active for a number of years. Earlier Chinese machines were also thought to be of questionable quality, but more recent machines have remarkably improved performance. A particular country of interest in terms of AM technology development is Israel. One of the earliest AM machines was developed by the Israeli company Cubital. Another company, Object, is successfully using droplet deposition technology to deposit photocurable resins. Well, with improvements in AM technology, the speed, quality, accuracy, and material properties have all developed to the extent that parts can be made for final use and not just for prototyping. Certainly, we will continue to use this technology for prototyping for years to come, but we are already entering a time when it is commonplace to manufacture products in low volume or unique products using AM. Eventually, we may see these machines being used as home fabrication devices. In summary, AM technology got existed and developed with the help from the quick improvement of computer technology, also from innovations like areas like 3D graphics and computer-aided design software. The main technology associated with AM is CAD technology. There are a lot of exploring around them, like which kind of machinery works the best with it, or what is the best way to manipulate CAD file to generate the slice data for AM machine. There are also a lot of exploring in the field of other technologies related to AM, like laser technologies different using method, printing technologies development, materials made to work with AM better, and the combination use of CNC machinery and AM. For nowadays, the normal way we are using to classify AM processes is described by form, which uses a two-dimensional classification method. Since 1950 and 1960s, AM has started developing around the world and has been used widely. For now, we are expecting to see it being used much commonly in our daily lives with easier accesses. Okay, so I was aiming to make this presentation for like 10 minutes. Sorry for exceeded it for another 5 minutes. But this chapter really has so many great parts which I don't want to skip in order to sharing with you guys. Thank you for bearing with me. Thank you guys so much for watching. And since this is an online presentation, you are welcome to ask questions with your comment or email me. All is good. All right. Thank you guys and bye bye.